We've talked about permutation matrices before when we talked about row exchanges in the process of elimination. We mentioned that sometimes a matrix cannot be brought into an upper triangular form via elimination, or elimination fails if we need a row exchange. And this is how permutation matrices came about. And that's exactly what a permutation matrix is. In fact, the formal definition of it is a permutation matrix P has the rows of the identity in some order. If we want to find, for example, all, let's say, all permutation matrices of size 3 by 3. So, example, all permutation matrices of size 3 by 3. Well, the identity matrix is a permutation matrix. It's remember from high school when you talked about permutations. Permutations talk about orderings. In this case, we're talking about the different ways in which we can order the rows of the identity matrix. Well, you could just take the trivial order in which every row is in its rightful place. This too is a permutation matrix. So this is a permutation matrix. Another permutation matrix could be if we exchanged the first two rows of the identity matrix. I'll denote that with P12, sub 1, 2, to give us a hint that the first row is going into the second and the second is going into the first. So we have this shape for that matrix. Now another one could be rearranging the first and or exchanging the first and the third row. We would have the third row right here, the second in place, and the first right there. Looking very similar to a diagonal matrix, but we're not treating this as a diagonal matrix. Now, we could change P2, 3, and in fact, those are all these three matrices over here are the only matrices, permutation matrices where only a pair of rows is being exchanged. So the first row here stays the same, and then in the second row we have the third row of the identity matrix, and then in the third row we have the second row of the identity matrix. So these are an exchange of a pair of rows. We could also sort of bring all the rows into play. So we could take the first row into the second and the second into the third, and then the third row into the first. And we denote that with 1, 2, 3. So I start here, here, and then here. And finally, the last permutation that we have is where we take the first row into the third into the second, and the second into the first. These are also called cycles. So the first goes into the third. So we have a 1 here. Then the third goes into the second. So we have a 1 here. And the second goes into the first. You see, because there are 3 rows, all the possible orderings of 3 rows is 3 factorial, which is 6. So there are no more than, or these are all of the permutation matrices of size 3 by 3. Now pay attention to the following thing. All of these matrices are symmetric. Obviously, the identity is symmetric. It's a diagonal matrix. its diagonal is, you can think of it as a mirror. There are zeros above the diagonal, zeros below the diagonal. So this is a symmetric matrix. Sorry, I said something wrong. They're not all symmetric. This one is symmetric. This one is symmetric. And this one is symmetric. So when you change a pair of rows, you get a symmetric matrix. The other two are not symmetric. But what is interesting about them is that they are transposes of each other. So you have P1, 2, 3 transpose is P1, 3, 2. And obviously the transpose of P1, 3, 2 is P1, 2, 3. The interesting thing here is that for a permutation matrix, the inverse of remember, a permutation matrix rearranges the rows of the identity. Well, then its inverse is supposed to put the rows back, which is another way of rearranging the new matrix. So the inverse of a permutation matrix has to be a permutation matrix. Since all of these matrices, since all permutation matrices of size 3 by 3 are listed here, the inverses also have to be here. And the interesting property of permutation matrices is that their inverses are in fact their transpose. A very, very powerful property. If you know that a matrix is a permutation matrix, then you know its inverse right away. Its inverse is simply its transpose. How to see that the inverse is the transpose? Without going into a formal proof, let's just give it a try. So if I take, let's say, one of the matrices, you could even take one of the symmetric matrices. So I would have 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is a symmetric matrix. This is the matrix P. To show that P transposes its inverse, I need to multiply by it and check that I'm getting the identity. So this is what I'm trying to verify. P transpose is simply P. So I will multiply by P. 0, 1, 0, 1, 0, 0, 0, 0, 1. Now what is happening here is when I try to carry out the multiplication, I look at the first row and the first column. You see, the 1 in the first row is in the second is the second component of the first row, and it is the second component of P transpose. So this makes sense. Even though P equals P transpose, what is important is that the place where I have a 1 in P, in the first row of P, is the same spot where I have a 1 in the first column of P transpose. So when I take that product, I will get a 1. Now when I try to multiply the first row by the second column, the ones don't hit each other. Or they miss each other. I would have 0 times 1, 1 times 0, 0 times 0. The product would be 0. So I'm getting a 0 here. And similarly, if I did the second row times the first column, because that's like inverting the product, the dot product, which is the same. So I get a 0 here as well. What about, let's say, the third row and the third column? So I guess I should have continued here. The second row with the second column, when they meet, they give a 1. The second row and the third column, again, those ones miss each other, so we get a 0. Sorry, that was also true for the first row and the third column. Then second row and third column, we get another 0. And that's how we get these zeros as well. And then last row times last column is a 1. So we got the identity matrix. Since we got the identity matrix, it means that P transpose is indeed P inverse. Let's do one more example where we take this, let's say P1, 2, 3, where we have a 1 here, a 1 here, and the 1 here. I'll add the zeros just so we can see better. Now, this is P. Its transpose, I have to take the rows of P and write them as columns. 0, 0, 1, 1, 0, 0, 0, 1, 0. Let me use a highlighter. This row is the same as this column. This row is the same as this column. And this row is the same as this column. And because they are the same and they have only one non-zero term, when you take their dot product, you get a 1. So we definitely have 1s along the diagonal. Now, what is happening off diagonally when you take, say, the green row and the yellow column? Those ones miss each other. You get a 0. When you take the first row and the third column, the green and the orange, the ones miss each other. You get a 0. And similarly for all the other ones. So that's how we know that for permutation matrices, the inverse is simply the transpose. That is the easiest inverse you can possibly find. All right, that's enough for today.